Okay, our next way to make an amine is one of the most popular methods of making amines today, and that is reductive amination. And so reductive amination is where we take a carbonyl compound, a ketone or an aldehyde, and we convert it to an imine, and then we reduce the imine down to an amine. Okay, so you see here we have our ketone. You guys would remember catalytic amount of acid and ammonia, and that produces our imine. Okay, so you should remember that functional group, the imine. We would have seen that in the aldehydes and ketones section. Then we can reduce that using hydrogen and platinum like you see here to make an amine. Now, what's cool about this is that you can actually mix all of these reagents together, okay, and then you can subject it to the pressure of the hydrogen gas with the platinum catalyst. And so what it does is as soon as the imine is formed, it gets reduced in the reaction flask. So everything happens in the same reaction flask. And we call this in situ, which is just Latin for, so in situ just means in place. All right, so you get a 2-for-1. And besides doing this method here where you make the imine and then you subject it to hydrogenation, there's actually, it says here, accomplished via a variety of reducing agents. I would say there's even better ways of doing that. Yeah, so let's take a look at one. So here we go. Instead of using sodium borohydride as the reducing agent to reduce our imine, what we're going to do instead is we're going to use this brand new reagent called sodium cyanoborohydride. Okay, the structure is here. Okay, you can see the formula is here. So sodium cyanoborohydride, and you can see that the only difference between sodium cyanoborohydride and sodium borohydride is that you replaced one of the hydrogens with a nitrile, right? That's all you did. You replaced it with a cyano group. But you know that a cyano is electron withdrawing. So since this is electron withdrawing, it stabilizes the negative charge on the boron, which renders this a weaker reducing agent than sodium borohydride. So you see here it says sodium cyanoborohydride does not react with ketones or aldehydes. Sodium borohydride does, doesn't it? Right? So it's a weaker reducing agent, but it does react with imines. So if you mix this up in the reaction flask with your ketone or your aldehyde, it's not going to touch it, okay? But as soon as the amine is formed, it's going to reduce it. And so the reaction is done in situ. Okay, so the reduction is done as soon as the amine is formed. The sodium cyanoborohydride comes in and reduces it. So this is a one reaction synthesis. So it's a really great thing. You can put everything in the same reaction flask, start with your ketone or aldehyde, and end up with your amine. And so here's what the reaction conditions are going to look like, okay? We have our ketone or aldehyde. Now let's say we used ammonia as our amine and a catalytic amount of acid in sodium cyanoborohydride. Well, we're going to replace the oxygen, right, with the one nitrogen, right? NH2. Now we have an NH2 group, so we've made a primary amine. What if instead of using ammonia, we use a primary amine? So again, this is ammonia. So ammonia produces a primary amine. But what if we have a primary amine as the nucleophile in our flask? Okay, it's going to react with the ketone, with the catalytic amount of acid. It's going to make the imine, and then the imine is going to be reduced by the sodium cyanoborohydride. And so now the primary amine is going to end up synthesizing a secondary amine, and you can see where this is going. So then if we have a secondary amine in our reaction flask, it's going to react with our carbonyl, aldehyde or ketone to make our imine, and then that's going to get reduced reduced by the sodium cyanoborohydride. And now we end up with a tertiary amine. So you can see the trend here. If you use ammonia, you get a primary amine. If you use a primary amine in your flask, you get a secondary amine as your product. And if you use a secondary amine as a reagent, you end up with a tertiary amine as your product. Now, the best way to master reductive amination is to practice it. So this question asks us to show two different ways of preparing each of the following compounds by reductive amination. If we look at the first compound, you've got two propyl groups and a methyl group, right? These two bonds are identical, right? And then you have this bond here. So either one is fine, but let's say we wanted to start with the blue, okay? So that means we would need a carbonyl, right? We would need a carbonyl coming off of here, okay? So what would our aldehyde look like? Well, it would only have 3 carbons, so that's propionaldehyde. So we'd have propionaldehyde like this, okay? And then our amine is going to be all the rest of this, okay? So we're going to have our catalytic amount of acid, our sodium cyanoborohydride in our reaction flask, and we're going to have that amine. So I'm going to draw it the same way it's shown here, like this. Then we just need a hydrogen, okay? And that is going to give our desired product. So we've got our, maybe I'll use a black pen for the product. Anyhow, we've got our methyl group, then we have 1, 2, 3, 1, 2, 3. There we go. So that's the first method. Now, if I wanted to I'll use a red pen now. If I wanted to use this as my amine, well, what would my carbonyl look like? Well, it would only have 1 carbon in it, right? So it would be formaldehyde would be my starting material. And so in that case, let me just erase some of the spinach here. I'm going to start it with formaldehyde. So formaldehyde, the simplest possible aldehyde we can have. And then I'm going to treat it with sodium cyanoborohydride, catalytic amount of acid. I think we normally list that first in the textbook. It doesn't matter, but I'll just try to be consistent here so I don't confuse anybody. There we go. And then our amine, 1, 2, 3 carbons. 1, 2, 3. There we go. And so since we're making a tertiary amine, you can see that both of the amines that we use, right, secondary amine and secondary amine. So there you go. So that's how we could make this compound a couple of ways by reductive amination. All right, C is a little more interesting because we have a ring, but you can see we've got a carbon-nitrogen bond here, so we could break that one. And we've got a carbon-nitrogen bond here, so we could break that one. Either one, we could have the carbonyl coming from it. So if we start with, let's say, the blue one, okay, let's imagine we had the carbonyl here, okay? Now we're making a secondary amine, so that means we're going to start with a primary amine. And just to make things simpler for me, I'm going to count my carbons here. Maybe I'll use the green pen for this. So 1, 2, 3, 4, 5, 6. And then the nitrogen is going to be the 7th atom in that string of atoms, so to speak. So I'll use my blue pen here and we'll say, okay, we're going to have our carbonyl. So that's 1, 2, 3, 4, 5, 6. And then I'll put the nitrogen like this and I'll just put NH2 like that. So there you go. So if we took our catalytic amount of acid and our sodium cyanoborohydride, that's going to give us our product. Now keep in mind, this is an intramolecular reaction, right? This is an intermolecular. Inter is between 2 different molecules, but this is in the same molecule. So you've got the amine and you've got the carbonyl, the ketone, built into the same molecule. Okay, so that's intramolecular. Maybe I should write that down here. Intramolecular. Okay, intramolecular reaction. Okay, so let's say if we wanted to make the carbonyl on the other side, right? If we had our carbonyl here, okay, then our amine would be tied to this carbon here. And so I'll use my red pen for this one. So we're going to have 1, 2, there's our amine. So we've got 1, 2, 3, 4, 5, 6. And on the 6th, we're going to have our carbonyl. So in this case, it's going to be an aldehyde. And so the reagents are going to be the exact same. We treat this with a catalytic amount of acid and our sodium cyanoborohydride. There you go. So reductive amination, again, we could do it either way. Either one of these is fine, and these are both intramolecular reactions. Okay, and for D, hopefully you can see the trend here now. We've got these types of bonds here. Those are both identical. And then you have this one here, which is different. So let's start with the blue. I think that one's actually a little less complex, okay? In that case, let me get my blue pen. Our carbonyl is going to be here, right? That's where the carbonyl would come from. So we're going to start out with our ring, which has the nitrogen incorporated in it. Then if we count off here, we have 1, 2, 3, 4. So we have 1, 2, 3, 4. And so I'll just dangle the aldehyde up here like this. So, and we can just write down our reaction conditions. Acid catalyst, sodium cyanoborohydride, like that. That's going to give us our product, which is this bicyclic product, which has a total of what? 10 atoms in the bicyclic system, like that. Okay, now if we broke it where the red bond is, so let me erase some of this scribble that I had here. Okay, there's a number of ways you could draw this. I'm going to show you what I think is the easiest way to do it. So if we did the red way, right, the carbonyl, where's my red pen? The carbonyl would be here, right? So I honestly think, and you might laugh at the way I draw this, but I think this is the easiest way to do it. So remember, we're making a tertiary amine, so we're going to have to start with a secondary amine. So we've got 1, 2, 3. So I think drawing it like this is a little bit ridiculous, but it helps, okay? And I think if you look in the solutions manual, he draws it slightly different. But if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have the right number of atoms. And so there you go. All right. So again, same old conditions, right? The more you repeat them, the easier they are to remember. So catalytic amount of acid, sodium cyanoborohydride. And there you have it. So reductive amination, very important chemistry. And what's neat about reductive amination is that chemists use it to make what are called libraries of compounds now. So they'll pick, maybe 100 different amines and 100 different aldehydes and ketones, and then they'll run them in a grid of reactions, right? So they'll have all these different aldehydes in different vials here, and then they'll have all these different amines in different vials here, right? And then they just crisscross them, right? And you'll have a robot, like a liquid handler, that runs all these different reactions. And so you can make hundreds of compounds in a day. The difficult part, I guess, would be purifying them, but there's robots that can inject these into what's called a high pressure liquid chromatography, and they can purify them and then run the mass spec on them in NMR. Anyhow, there you go. So reductive amination. There's many different reagents that can be used for reductive amination, but sodium cyanoborohydride is probably the most popular, most common. So there you go. Okay, question 22.15. Methamphetamine, crystal meth, is used in some formulations for the treatment of ADD. Can be prepared by the reductive amination using phenylacetone and methylamine. Draw the structure of methamphetamine. You might remember there was a whole TV show devoted to the synthesis of methamphetamine, and I think that in one of the episodes maybe they were talking about phenylacetone and where are we going to get phenylacetone. And then if you do a reductive amination between phenylacetone and methylamine, then you end up with methamphetamine. So let's figure it out. First of all, acetone. What's acetone? Acetone is a compound you should know by now. It is propanone. It's the simplest ketone. So this is acetone. And so phenylacetone just means we take acetone and we put a phenyl group on one side. Okay, so we replace one of the hydrogens with a phenyl and we get phenylacetone. So now you know what the structure of phenylacetone is. So it says it's a reductive amination between phenylacetone, so that's our carbonyl, and methylamine. And methylamine is straightforward enough, right? Methylamine is just CH3NH2. And so we're going to use a catalytic amount of acid, our sodium cyanoborohydride, and our methylamine. So I'll just use the condensed structure there. And so the structure of methamphetamine is going to look like this. And so there you go. So this would be methamphetamine. All right. So now you know methamphetamine synthesis.